Hello gems! Welcome back to another video. In this video, we'll be discussing the previous year Bitsat questions from the chapter of ray optics. Now, ray optics is the last topic that we are discussing, which also means that A series is coming to a happy ending, which also means that we have discussed all the previous year questions from all the chapters. Okay, so if you have missed any of those, you can check out the description box of this video. You'll find a playlist over there. And thank you so much for supporting this series. Let's begin with today's video. So here we go. We have question 1, 2, 3, 4 from the super easy category. So let's go. Question 1, time taken for light to cross 4 mm of glass. Okay, the refractive index of glass is given. A very simple question. You are just asked for the time. So time will be given as distance upon speed. Right, now here the distance is given, which is nothing but the thickness of glass, right? And you are just supposed to find the speed in order to calculate the time. So how will you find the speed of light in glass? Okay, now you are given the refractive index. How is refractive index defined? It's defined as the ratio of speed of light in vacuum divided by the speed of light in the particular medium, right? So we are supposed to find this V over here. So V will be given as C by mu, right? C is 3 into 10 to the power 8, that is speed of light in vacuum, and divided by mu, which is 1.5. So 1.5 2s are 3, right? So the speed of light in glass is 2 into 10 to the power 8. Okay, now from here we can find the distance easily now. No, sorry, the time easily now. So distance is 4 millimeters. So 4 into 10 to the power minus 3 meters. And here we have the speed in meters, which is 2 into 10 to the power 8. Right, so 2 will cancel with this. So you get 2 into 10 to the power minus 3 and this minus 8, that will become 2 into 10 to the power minus 11. Okay, so this is the time taken for your light to go across a glass which is 4 millimeters wide. Okay, let's come to question number 2. When light refracts, the quantity that does not change. Okay, it's a very theoretical question. It's easy to see that the frequency is the one that does not change, right? Frequency is something which depends only and only on source. Okay, it does not depend whether the ray is reflecting or refracting. Okay, whenever a ray refracts, frequency will not change because it is something which depends only and only on source. Whereas if you see velocity, of course, going from one medium to another, velocity of course changes, right? In vacuum this, in glass something else, in air something else, in water something else, right? So velocity changes. Wavelength will also change, because if you see the relationship between your velocity and frequency and wavelength is this: frequency is not changing, wavelength, so velocity is changing, which means your wavelength should also change. Okay, amplitude, if you see in refraction, there is also reflection involved, right? All of the rays are not completely refracted, some part of it is reflected, so there is loss in intensity, so amplitude will of course change. Okay, the only thing that is not changing is frequency, because it only depends on the source. Okay, that is the answer in short. Let's come to question number 3. Air bubbles in water shine due to. Now let's see this. Okay, so suppose we have water over here and air bubble in that water. Okay, so rays coming from water, actually what happens over here is that are traveling from denser to rarer medium. Okay, so there is a chance of total internal reflection happening over here, and that is what is actually happening over here. Okay, so rays are traveling from a denser medium water to air bubble, which is rarer medium. So they hit occasionally at an angle which is greater than critical angle. Okay, so this angle sometimes is greater than critical angle, and some of these rays, okay, I shall say all of those rays which hit at an angle greater than critical angle will be reflected, right? Not refracted. So this air bubble kind of reflects the rays, right? Just like a mirror. So that's why it shines. Okay, so the correct answer over here, the phenomena that is happening over here is total internal reflection. Okay, and due to which your air bubble reflects the light, and due to which it shines. Okay, because it reflects like a mirror, that's why it shines. Okay, so coming to question number 4, resolving power of a telescope is more if the diameter of the objective is. Now, I remember I told you about this in the previous class too. I don't know resolving power if it's a topic of wave optics or ray optics, but those questions are also important. You'll see the questions on resolving power and limit of resolution being asked in Bitsat. Okay, so please don't skip over those topics. Those are also important. At least by heart the formula. Okay, so resolving power, the formula is basically uh, a upon 1.22 lambda. Okay, a is basically the aperture, or I can loosely call it the diameter. So you can easily see that the resolving power is directly proportional to your aperture or diameter. So larger your diameter, the larger will be the resolving power, majorly because the angular separation increases and your image is resolved very properly. Okay, anyways, you are not asked for the reason. The answer over here is larger. Okay, so larger the diameter, the larger the value of a greater will be the resolving power. Okay, so that's all from the super easy category. We'll step up the levels now and let's move to the easy category. So question number 5 from the easy category this time. This is a question from 2018, the most recent question that we are going to see today. Okay, so from the diagram you can make out it's a question from refracting from a spherical surface. Yes, so in this question we have an object which is placed at a distance of 15 centimeters from this reflecting surface. The reflecting surface is made up of glass. A refractive index is given. You are also given that the radius of curvature is 30 centimeters. You are supposed to tell where will be the image formed, right? So there is a direct formula for this one, which is mu2 by v minus mu1 by u is equal to mu2 minus mu1 upon r. Okay, now you have to be very careful when you're placing the values of mu2 and mu1. I know some of you might have uh, mug this up using when the object is in rarer medium, this is the formula, and when the object is in denser medium, the formula is just to change mu1 and mu2. Okay, I know that is right in most of the cases, but whenever you'll have virtual objects, that formula will fail. Okay, so the best way to remember is that mu2 is the medium where the ray visits the second time. Okay, so if you see in this case, this will be mu1 and the glass medium will be mu2, because that is the medium the ray visits second. Okay, first the ray is in the air medium, right? This is air and this is glass. Okay, the ray will visit the glass medium second. So mu2 is the refractive index of glass. Okay, mu2 is the refractive index of that medium which the ray will visit second. That is the way to remember what value you have to plug in for mu2 and what for mu1. Okay, so mu2 will be refractive index of glass, which is 1.5. V is something that we have to find, where is the image formed, minus mu1, it's air. Okay, so that is 1 divided by u is 15, minus 15, right? Distance is measured from the pole and opposite in the direction of your incident ray, then it is negative. Okay, so please remember the conventions. So it is minus 15. Okay, now next thing is mu2 minus mu1, so 1.5 minus 1, that will be 0.5 upon r. Okay, upon r. Now if you see, r will be measured in this direction, right? You just have to complete this sphere and the radius will be measured in the direction of the incident ray, right? So it is positive, so it will be plus 30. Okay, so we just have to solve this now. Okay, so this is 1 by 15. Okay, and here we'll have shall we cancel this? Okay, we'll keep it as it is. So 1.5 by v is equal to 0.5 by 30 minus 1 by 15. So 30 is the LCM. 0.5 minus 2. Okay, 0.5 minus 2 is minus 1.5. Okay, so 1.5 divided by v, this and this will get cancelled. So v is minus 30 centimeters. Okay, so the image is actually formed on the left hand side. Okay, it's minus 30, right? So it's on the left hand side, opposite to the direction of the incident ray. Incident ray is going this way, this direction is positive, this direction is negative. Okay, so minus 30. So the image is formed somewhere over here. Okay, here is the image. So 30 centimeters left is the correct choice over here. Okay, so I hope the approach is clear. Mu2 is the refractive index of that medium in which the ray visits the second. This is the sentence to remember. Let's move to the next question. So question 6 over here. In this question, we have a biconvex lens. R is 20 centimeters on either side. Object is placed at a distance of 30 centimeters from your lens, okay? And HO, the height of the object, is 2 centimeters. You are supposed to tell what is the nature of your image, whether it's virtual or real, and you are also supposed to comment about the height of the image, okay? And here the refractive index of lens, it's made up of glass and it is given as 3/2, okay? So let's try doing it. So the basic thought process behind this is that we'll go for magnification, okay? Magnification is given as V/U, right? So first we have to find V, okay? Where is the image? We have to find V. From there we'll find V/U, which is magnification. Magnification positive means the image is virtual. Magnification negative means the image is real, right? I hope you know it. And from there we'll also get a factor as how big is our image with respect to our object, okay? So let's stop discussing about it and let's start doing. Okay, so the first thing we are supposed to find is V, okay? So we can find V by using this formula, right? This is the lens formula. 1 upon f is equal to 1 upon v minus 1 upon u, or the intellectuals can use v is equal to u f upon u plus f, okay? Just made v a subject from here, okay? So now what is the value of f? F is 20/2, is it? No, it's not, okay? Please remember this, that your f is r/2 only for mirror, okay? So f is equal to r/2 for mirror, okay, not for lenses, okay? This is not true for lenses, okay? So how do you find f for lenses? Lens maker formula, okay? So please remember that your f is not r/2 for a lens, okay? Don't do a silly mistake like that. So 1 by f will be 1 minus mu, the lens maker formula, 1 upon r1 minus 1 upon r2, right? Here mu is given as 3/2, right? The surrounding medium is air, so does not make any difference. It will be just 1 in the denominator, and then 3/2 minus 1, 1 divided by r1. Now r1 is, suppose we have this biconvex lens, okay? R1 will be the radius of this sphere, okay? It's in the positive direction, right? Going in the direction of the incident ray, so it will be positive 20, okay, minus 1 by r2. R2 is this, the radius of this sphere. It is, the radius is in this direction, right, opposite to the direction of incidence, so that is negative, okay? Some of you might directly by heart that r1 is positive for biconvex and r2 is negative. Anyways, okay, so this was negative over here, this is also negative, so I just made it positive, okay? So 3/2, which is 1.5 minus 1, that is half, so half. And here we'll have 1/20 plus 1/20, that is 2/20, okay? So 2 and 2 will get cancelled, and f is itself 20, not 20/2, okay? Yes, so that is our answer for f, okay? So we get the value of f as 20, and it also shows that it's positive 20, so it's convex lens, right? It has a positive focal length, right? Now here u will be minus 30, right? The object is placed in this direction, opposite to the direction of incidence, at a distance of 30 centimeters, okay? So u is minus 30, and f we have found it as 20, okay? So minus 30 into 20 upon minus 30 plus 20, right? Minus 30 plus 20, which is minus 10. This and this will get cancelled. 32s are 60, okay? And that is positive 60. This is V, right? V is positive 60 centimeters. Okay, so the image is formed at positive 60. Okay, so from here we can actually find magnification, which will be V/U. Okay, so V/U. Okay, for lenses it is V/U. Yes, and 60/U is, if you see, where is U? U is minus 30, right? So here you get the magnification as minus 2. Okay, so the image is real because the magnification is minus 2. Okay, remember that real images will be inverted. Okay, so that is why we have the negative sign. Okay, so here magnification is negative, so the image will be real. So either it's option C or option D. You can see a factor of 2, so the image is twice the height of object. Object is 2 centimeters, image will be 4 centimeters. Okay, so option C, real and height will be 4 centimeters. Magnification, you can write it as hi by ho, right? So ho is 2 centimeters, take it to the other side, 2 to the 4, right? So the height of your image will be 4 centimeters in the opposite sense. Okay, that is what the negative sign is showing. Okay, so that is how you do this question. Okay, so I hope that is clear. Okay, you just had to reach till magnification, and from magnification you can conclude what is the nature. Okay, so let's move to the next question now. So question number 7 over here. In this question, we have two lenses. One is a plano-convex lens and the other one is a plano-concave lens. Okay, now their refractive indices are given and they fit together like this. Okay, so they have the same R. This was given in the question. In fact, you can make it out from here that they fit together means that this surface and this surface will have the same value of R. Okay, same radius of curvature. Okay. So yeah, that is given and you are supposed to find what is the equivalent focal length of this combination. Okay, let me repeat the question. What is the equivalent focal length of this combination? Okay, now the equivalent focal length has a very simple formula. What is that? 1 upon Fe is given as 1 upon F1 plus 1 upon F2, right? If we have two lenses. Okay, so for two lenses it is 1 upon F1 plus 1 upon F2, right? So if you see lens 1, okay, now we'll use lens maker formula to find 1 upon F1 and lens maker formula to find 1 upon F2. Okay, so 1 upon F1 is given as mu minus 1. Okay, here we'll consider that the surrounding material is air. Okay, so mu1 minus 1 for the first lens, right? The refractive index of the lens is mu1 minus 1 into 1 upon R1. Okay, R1, if you see the first, okay, R1 is where the ray will strike first. Okay, so this surface has a radius of curvature infinity, right? It's a plane surface, so basically the radius of curvature of that surface is infinity. And the second surface, if you see, has a value of R equal to R. Okay, so same R, and that is they both have same R, this surface and this surface, and it was given as R. Okay, so you can see that in the options too. Okay, so 1 by R2. R2, if you see, the sphere is like this, right? The sphere is like this. So in order to measure R2, you have to go opposite to the direction of the incident ray. Okay, so it's minus R. Okay, so minus and minus will become plus, and you'll have this. Okay, so 1 upon F1 is nothing but this is infinity, right? Plane surface, radius of curvature infinity, so this is 0 and you'll have mu1 minus 1 upon R. Okay, and if you see for lens 2, okay, let's discuss it for this lens. Okay, so here we'll have 1 upon F2, again applying the lens maker formula, will be given as mu2 minus 1 into, okay, 1 upon R1. If you see R1 for here, R1, this surface, right? So again this sphere, right? And again we have to measure the radius opposite to the direction of your incident ray. So it is minus, so 1 upon minus R, right? And R2, this is the second surface that your incident ray will strike, and it is a plane surface, so it is infinity. Okay, yes, so we'll get 1 upon F2 as mu2 minus 1 upon minus R, mu2 minus 1 upon minus R. Okay, so you just have to find the equivalent focal length, so which is basically the sum of this plus this. So you just have to add these two equations. So Fe will be given as F1, which is this mu1 minus 1 upon R, plus, okay, this R is same in the denominator, so I can just add them, R. Okay, I'll take this minus sign over here. Okay, so it is mu2 minus 1, right? So add this mu1 minus 1 minus mu2 plus 1 upon r. This and this will get cancelled. 1 upon fe, or fe will be given as r, just take the reciprocal, r upon mu1 minus mu2, which is option A. Okay, so r upon mu1 minus mu2 is the correct choice over here. Okay, this is the formula for combination. The finding the equivalent focal length, we found the focal length of lens 1 and lens 2 using lens maker formula, right? And then substituted this over there and simplified and got our answer. That is the simple way of doing it. Let's get to the next question now. So question number 8 over here, this is the question that has repeated twice in 2011 and 2018. So let's get to it. So in this question, we have a convergent lens with power 5 diopter. Okay, so plus 5 because it is converging. Okay, and it is given that the refractive index of the lens is 1.5. Okay, and this lens is now immersed in liquid. The liquid has a refractive index mu, and it is seen that the lens becomes a divergent lens. Okay, when you immerse this lens in a liquid of refractive index mu, it initially was a convergent lens in air, but now in that liquid it becomes a divergent lens. Okay, and now you are also told that it becomes a divergent lens with a focal length of 100 centimeters. Okay, or minus 100 to be precise, because it is divergent, right, like a concave lens. Okay, so it is minus 100. Okay, to be precise, you are supposed to tell what is the refractive index of the liquid in which you immersed it. Okay, so actually we can do this question merely by hack. Okay, so just remember this thing, that a lens will change its nature when immersed in a liquid only when the liquid has a refractive index greater than that of the lens. Okay, I repeat it again. So a lens will change its nature from convergent to divergent or divergent to convergent, okay, only when it is immersed in a liquid which has a refractive index higher than that of the lens. Okay, so if you see the refractive index of your lens is 1.5, let's see the refractive index of liquid over here. Okay, let's evaluate the different options and let's see which option are the options which are greater than this. Okay, those are something that we should look upon. Okay, so here if we see it's 1.33, right, 4 by 3 is 1.33, here it's 1.67. This is not bigger than 1.5, so it's out. This one is okay, it can be the answer. This one is 5 by 4 is 1.25. Yes, yes. So this is also out because it's less than 1.5. Okay, and 6 by 5 is 1.2, so again it is out. Okay, so the only correct choice over here is B. So you can just remember that a lens will change its nature when it is immersed in an liquid which has a higher refractive index than that of the lens. Okay, but I know you are not yet convinced. Okay, this was a hack way of doing it, right? So what if we had more than one options which had values greater than this? Okay, what in that case? Okay, so what is the conceptual way of doing this question? The conceptual way is of course using the lens maker formula. Okay, again, yes. So 1 upon f is, first we'll use it in air. Okay, so 1 upon f is mu minus 1. Okay, mu of lens minus 1. Surrounding is air, case 1. Okay, so this is case 1. Surrounding is air. We are told nothing about R1 and R2, so let's keep it as it is, 1 upon R1 minus 1 upon R2. Now let's come to case number 2. Okay, now before that, let's substitute this. 1 upon f will be your power, right? 1 upon f for a lens is power. Okay, so 1 upon f is 5, right, when the focal length is placed in meters. Remember that. Okay, so mu minus 1, 1.5 minus 1 will be 0.5, and 1 upon r1 minus 1 upon r2. Okay, so actually you can cancel this as 0.1. 0.1 will come over here. So 1 upon 10 is equal to 1 by r1. Sorry, 1 upon 0.1. So that is 10 is equal to 1 upon r1 minus 1 upon r2. Okay, so this is something that we get by solving the case 1. Okay, now let's come to case 2. Case 2 is wherein we immerse our lens in this liquid. Okay, so what happens now? 1 upon f, okay, f dash I will say, the focal length will change when you immerse it in liquid. Okay, so that's why it becomes divergent, right? So it will become mu L upon mu of the surrounding. Okay, in this case mu of the surrounding was air, it was 1, so I didn't consider it. Now here the surrounding is liquid of refractive index mu. Okay, so we have to consider it minus 1, and 1 upon r1 minus 1 upon r2. Okay, actually you could have written this and then just divided these two equations, but now we know that the value of 1 upon r1 minus 1 upon r2 is 10, so you can substitute it over there. Now 1 upon f is nothing but 1 upon 100 centimeters, right? Now remember that whenever we uh, write for power, right, power is 1 by f, where f is placed in meters, right? So for the first one we placed, when we placed the focal length, it was in meters, remember that. That's why we got 5 diopter. Okay, power in diopters is 1 by focal length in meters. Okay, here 100 centimeters, we have to make it in meters. Okay, so remember that, convert everything in meters, keep the units same throughout. Okay, so in this equation we have meters, everything in meters, or diopter you might say. Okay, so here also you want it in diopter, so the answer will be 1 upon 100 centimeters, no, 1 upon 1 meter. Okay, 100 centimeters is 1 meter, so it is 1 diopter. Okay, so basically 1 upon f is 100 centimeters, 100 centimeters is 1 meter, which is nothing but 1 diopter. Okay, and 1 diopter, and it is divergent. Okay, it's not convergent, it's divergent, so the power is negative. Okay, so there is a lot to think about this question, right? So yes, so it's divergent, so the power is negative. For convergent lenses the power is positive, for convex lens it's positive, for concave it's negative. Okay, for divergent lenses it is negative. Okay, so mu L is again your lens, which is 3 by 2, and mu we don't know, we have to find it, minus 1, 1 upon r1 minus 1 upon r2, we have it from equation 1, which is 10. Okay, now let's solve it. So this will become, when you get 10 over here, it will become minus 0.13 by 2 mu minus 1. Okay, so you can get 1 to this side, that will become 0.9. 0.9 is equal to 3 by 2 mu, or you can get mu onto this side, that will make 3 by 2 is 1.5 divided by 0.9, so the answer will be greater than 1.5, which is 1.67. Okay, option B, or you can directly see it, cancel it by 3, 3 5s are 15, 3 3s are 9, right? So just shift the decimal, multiply 10 first of all in the numerator and denominator, and then 3 5s are 15, 3 3s are 9, so 5 by 3 is the correct choice over here. Okay, so much of math or a little bit of logic, you decide. Okay, so let's move to the next question now. So question 9 over here from 2012. In this question we can see a glass, water and air interface. Okay, so you can see the path of an incident ray over here. Okay, so it goes through glass, it gets refracted at the glass water interface, and then it strikes the water air interface, and then it undergoes grazing emergence. And what does that mean? It undergoes TIR, not exactly TIR. TIR will happen if the angle is greater than R. Okay, so it is grazing the surface, the refracted ray is grazing the surface between air and water. Okay, so or the angle of refraction, I can see it as 90 degrees. Okay, so you are asked for the refractive index of glass, you are given the refractive index of water. Okay, so how will you go about this question? It's very simple actually. First, you can see that at this surface, okay, this first surface between air and water, we have grazing emergence which is happening. Okay, and in this case you'll know that the sine of your angle, sine of this angle, is nothing but 1 by mu, where mu is the refractive index of the denser material. Okay, basically I'm saying that the sine of the critical angle here, if you see, r is nothing but the critical angle, it is the angle at which grazing emergence is happening, right? So r over here is nothing but critical angle, so sine of critical angle is 1 by mu, right, where mu is the refractive index of the denser material, right? So whenever light goes from denser to rarer medium, there is a chance of grazing emergence and total internal reflection. Okay, so in case of grazing emergence, please remember this relation. Anyways, you can just apply Snell's law, treating your angle of refraction as 90 degree, and that will give you the same relation. Okay, anyways, so sine r will be nothing but sine r, okay, 1 by mu. So 1 by mu, denser material, which is the denser one, air or water, water. So water has refractive index 4 by 3. So 1 upon 4 by 3, that is 3 by 4. Okay, sine of r is nothing but 3 by 4. That is what we get. Okay. Now what we'll do, we'll apply Snell's law over here. Okay. And that will give us our answer. Okay, because we know sine r now. And sine I, we want to find the answer in terms of sine I. Mu g, yes, that is our unknown, and we have mu of water. Okay, so let's apply Snell's law on second surface. So here we apply Snell's law. Okay, so mu of glass into sine of this angle, sine of I, okay, is equal to mu of water into sine of this angle. Okay, so mu of this into sine of this, mu of this into sine of this, right? That is Snell's law. So mu of water into, or I just write it as mu to sine of r, right? Mu of this into sine of I, mu of this into sine of r. Okay, so mu of glass is something which we want to find, sine I is something which we don't know, and we want the answer in terms of sine I. Mu of your water is 4 by 3, sine of r is 3 by 4. Okay, actually you could have done this question by directly ignoring this layer and directly, but that would have been heck, but this is the right way of doing it. So yeah, the answer is, or the refractive index of glass is 1 by sine I. Okay, so what did we do? First, we found out sine r, we realized that r is the critical angle, and using the critical angle relationship, which is sine c is equal to 1 upon mu, where mu is the refractive index of the denser material. So sine r is equal to mu, and substituted mu, we found out sine r. We used the sine r over here, right? We applied Snell's law over here and used sine r and value of mu and got our answer in terms of sine. Okay, so 1 upon sine I is the correct choice over here. Okay, so let's move to the next question now. So question number 10 over here. In this question, we have a fish, okay, which is 12 centimeters below water level. Okay, so that fish will be only be able to see a circular region of the outside world. We'll come to know why, but for now, take the word that it will be able to see only a circular region of the outside world. You are supposed to tell what is the radius of this circular region. Okay, so now let's come to why. Okay, why will the fish only see a circular region? Why not the entire world outside? Okay, so the reason is that total internal reflection. Okay, you can see that the rays, okay, from fish eyes will move from denser medium to rarer medium. Okay, so there are chances of total internal reflection happening, and it is happening in fact. Okay, so here we have the water, here we have the fish. Okay, so if you see, rays are going from fish to the outside world. Okay, so here, suppose this angle, you can see that this angle will be I, okay, angle of incidence. Okay, this will be also I, right? These are alternate angles, these are two parallel lines, and these are alternate angles, right? So you can see that as this angle goes on increasing, right, as this angle goes on increasing, the angle of incidence also increases, right? As this increases, this also increases. Okay, so there will be a point where this angle, the angle of incidence, crosses the critical angle, right? And that time the ray won't escape out. In this case, it will escape, suppose, and this, suppose the angle is greater than critical angle, then it will get totally internally reflected, right? So that time the rays won't go out, and that region cannot be seen. Okay, so that is why the fish will only see a circular region. What is the maximum point that it can see? It can see from the normal, okay, to a cone like region. Okay, so a cone like region until your ray grazes the surface. Okay, so till critical angle, your fish can see the outside world. Okay, actually before the critical angle, so we'll consider this angle as C. So at C, this is the case, right? And here is the circular region that your fish can view. Okay, so you can easily see that it's kind of a cone. Okay, yes, so when your angle of incidence is equal to critical angle, there is grazing emergence, right? And after that, light is internally reflected, so it cannot see the outside world, right? So this is the maximum circular area that the fish can see. Okay, so let's find out this. Okay, so let's find out the radius of this. This is also C, right? This is C, then this is also C, because alternate angles, right? So you can write tan of C from this triangle. Okay, so tan of C, that will help us find R, right? That is what we are supposed to find. So R upon 2L, right? So opposite upon adjacent, this is the angle C. Here the light will graze this surface. Okay, so yes, tan of C will be R by 12. So R by 12. Now we want to find R, so 12 tan C will be R. Now how to find tan C? We can use the relation for critical angle. We know that sine of C is 1 by mu, where mu is the refractive index of the denser material, right? When the ray is moving from denser to rarer medium, there are chances of total internal reflection happening, and sine of the critical angle is given as 1 by mu. Mu being the refractive index of the denser material. Okay, so sine C will be given as, if you see 1 by mu, so 1, it will be 1 by 4 by 3, so which is 3 by 4. Okay, so this is the value of sine C. Now you can draw a triangle. Okay, this angle C, this is 90, this will be sine C. Suppose you want sine C as 3 by 4, how can you do that? So opposite upon hypotenuse, right? So sine C is 3 by 4 in this triangle. And let's find out this side. This side, how will you find? Using Pythagoras theorem, right? A square plus b square equals c square. Then find out this side. It will be basically under root 16 minus 9. Okay, I'm doing little bit of math, so it is root 7. Okay, so this side will be root 7. Okay, I just use the Pythagoras theorem. Now you can find tan C from here. Tan C, very simple, opposite upon adjacent, so 3 upon root 7, and substitute it over here to find R. Okay, so that will be 12 3s are 36 upon root 7. That is the value of R. Now there is also a formula for this, but I'll go by the approach. Okay, some of you might directly know the formula, well and good, but this is the approach how you do it. First of all, the fish cannot see the entire world outside because of total internal reflection. I hope you got the point. Okay, now the maximum it can see is this. Okay, this is the condition, right? Then we found tan C. From tan C we can find R. Okay, so before that we need the value of tan C, so we use the logic of our critical angle, right? So that is how we do this question. Let's move to the next question now. So question number 11 over here. In this question, we are going to cut a lens. Okay, so like this and like this to generate this 1, 2, 3, 4 piece. And this pieces will arrange them in contact like this 1, 2, 3, 4. And you are supposed to tell what will be the equivalent focal length of this combination. Okay, given that the focal length of your initial lens was f. Okay, so equivalent focal length, as you know, is given as 1 by f1. Here it will be given as the sum of all this. Okay, the sum of the reciprocals of all of this. Okay, so this will be the equivalent focal length, right? Now there are some results from cutting of lenses. Okay, one result says that when you cut a lens vertically like this, the two pieces that you generate like this and like this, okay, these two pieces will have, suppose the focal length of the lens that you cut was f, these two pieces will have focal length 2f. Okay, now there is a derivation behind this, which if we discuss now, it will be too much. Okay, it will take a lot of time. Now basically you can see this combination, you can combine this and it will give you the focal length of this lens. Okay, anyways, you can remember it directly that when you cut a lens vertically, okay, the focal length of the individual pieces becomes 2f 2f each. Okay, and what happens when you cut a lens horizontally? No change. Okay, so this and this lens will have the same focal length f. Okay, basically this piece will also converge the rays which are parallel to it at the same distance, right? When you cut it like this, there is no difference. Okay, so it will also converge it at the same point. That's why the focal length does not change. Okay, whereas in this case it becomes double. Okay, now in our case we are going to cut it horizontally and vertically as well. Okay, so the order actually does not matter. You can go vertically and horizontally, first vertical then horizontal, or first horizontal and then vertical. Okay, order does not really matter. Okay, so let's uh, cut it first horizontally. Okay, so when we cut this lens horizontally, we have f and f, right? When we cut it like this, we have f and f, right? Now let's cut each of this piece vertically. Okay, so we'll have the this pieces, piece 1. Okay, this will become 2f. Again, piece 2 will also become 2f. When you cut it vertically, it becomes 2f, right? It becomes twice of the original focal length, right? Here also when you cut this is piece 1, this is piece 2, here we have piece 3. Okay, it will also become 2f. Okay, and here again piece 4 will become 2f. Okay, so we have 4 pieces with focal lengths 2f each. Okay, so the combination basically will be 1 upon 2f, 1 upon 2f plus 1 upon 2f plus 1 upon 2f. So 4 times 1 upon 2f. Yes, and we can cancel this as 2 times. So 1 upon fe is 2 by f, or fe is f by 2. Okay, so the correct choice over here is f by 2. Okay, so just remember that when a lens is cut vertically, the focal length become twice, and here when it's cut horizontally, it does not change. Okay, so first we cut it horizontally, does not change ff. When we cut it vertically, it does change to f to f to f to f. Okay, and now those all of those 2f in combination, 1 upon 2f plus 1 upon 2f plus 1 upon 2f, that is 4 times. And yeah, solve it and get your answer. Let's move to the next question now. So question number 12 over here. This question is based on telescope. Here you are given that the magnification produced by a telescope is 9 when the image is formed at infinity. You are also given that the length of the telescope, the distance between the objective and the eyepiece, is 20 centimeters. You are supposed to tell what are the focal lengths of your objective and eyepiece. Okay, now it's a very straightforward question because you are just supposed to know the formulas over here. Okay, so image at infinity, the magnification first of all is given as 9. So for image to be at infinity, the magnification formula is FO by FE. Okay, when the image is at infinity for a telescope, the formula for magnification is FO by FE. Okay, so from here you can see that FO is 9 times FE, right? And I got my answer from here. You can see that one is 9 times other, right? FE is 9 times, FO is 9 times FE, right? So it is in option A. No other option satisfies that. Yes, so option A is the correct choice over here. Anyways, that was just heck way of doing it. Now let's do it the way it is supposed to be done. Okay, now you are also given that L is 20 centimeters. Basically, we'll find two relations between FO and FE, solve them simultaneously and have our answer, right? So L is given as 20 centimeters. In case of image at infinity, L is FO plus FE. Okay, when the image is not at infinity, it is FO plus UV. But when the image is at infinity, it's FO plus FE. Okay, L, which is 20. Now FO, we can substitute it as 9 FE plus FE, and we have 10 FE is equal to 20. So FE is nothing but 2 centimeters. Okay, and FO will be nothing but 9 to the 80, right? So that is what I said. One is 9 times the other, right? So 18 centimeters and 2 centimeter is the correct choice over here. Okay, let's move to the next question now. So question number 13 over here, the first from the easy to moderate category. So in this question, we have a vessel whose depth is 2d, okay, where d is some distance. Half of this vessel is filled with a liquid of refractive index d. The other half is filled with a refractive index of with a liquid with a refractive index of mu2. Okay. Now, of course, these two are immiscible liquids. They do not mix with each other. You are supposed to tell what is the final apparent depth. Okay, so of course there will be shifting of the depth. Okay, the depth will rise due to these liquids. Okay, it depends whether it's denser or rarer, but yeah, there will be the shift in the depth. Okay, and you are supposed to tell what will be the final apparent depth due to these two liquids. Okay, so first of all, let's assume we have some object over here. Okay, let's see how much does that object shift. Okay, so first we'll consider this surface number 1. Okay, let's see, this d will be the actual distance over here, and suppose we say that the image is formed over here. Okay, right, mu1 over here, and suppose we say that the image is formed over here. So this is nothing but the apparent depth. Okay, in wherein we are seeing the first surface only. Okay, we also have to go for the second surface and then combine it. Okay, so for the first one it is d dash. Okay, and the actual depth from here, okay, from the surface is d, right? You measure actual depth from the surface, depth and apparent depth from the surface. Okay, so the surface that we are considering over here is this one, right? So for this we have a formula. I remember it this way, that coming upon going. Okay, so coming upon going is equal to real upon apparent. Okay, so basically where if you see this surface, okay, so where is your ray coming from? It's coming from mu1, right? So mu1 upon where is it going? Mu2. Okay, real depth is capital D, right? You measure depth from the surface, so from here to here, capital D divided by the apparent depth, which we have considered as d dash. Okay, so d dash from here will be mu2 by mu1 into d, right? Mind you, this is not the final apparent depth, right? This is only due to surface 1. Okay, let's consider surface 2 now. Now for surface 2, it is must to remember that this will act as an object. Okay, now the object is over here, of course, but it has shifted due to this liquid, right? Now the image of this object will act as the object for the second liquid. Okay, I'll say that again. The image of the object will act as the object for the second liquid. Okay, so basically we have our object. I'll write it O dash. Okay, because this image of this object is acting as object for the liquid 2. Okay, I know that confuses you a lot, but we'll see where we have to use it. Okay, so we have surface number 2, and on the other side we have air. Okay, so again, coming upon going, so we have the rays coming from mu2, so coming is mu2, going is air is 1. Okay, refractive index of air is 1, we consider it 1. So it is real upon apparent. Now what is the real depth? Okay, real depth of the object. Now what is the object? This is the object. O dash is the object for liquid number 2. Okay, so this is the object. What is the real depth now? D plus D dash, right? The depth of this object is D plus D dash. Okay, so that is the point that you have to carry. Okay, so the depth over here is D plus D dash. That is the real depth. Okay, so next thing we have the apparent depth. We'll name it D double dash. Now this is the thing that we are supposed to find, right? That this will be the final apparent depth. Okay, so finally we'll have, suppose, the object somewhere over here. Okay, so this will be D double dash. Okay, so that is what we are supposed to find. That is the final place where we are seeing the surface or the apparent depth over here. Okay, so that is the final thing that we are supposed to find, D double dash. Okay, that is our final apparent depth. Okay, so D double dash will be nothing but 1 by mu2 into D plus D dash. Now D will keep it as it is. D dash, you can write it from here, it is mu2 by mu1 into D. Okay, now I know this question seems a lot difficult to understand, but yeah, you can go again through it and try understanding it second time. Okay, you can always rewind whenever you don't understand. Now taking d common, you can write it as 1 upon mu 2, or I'll write it as 1 upon mu 1 plus 1 upon mu 2. You just multiply this inside and bring d out. Okay, so the correct choice over here is option B. Okay, I want you to remember this result directly by heart. Okay, so you can remember, actually you can generalize it more, that final apparent depth in case of multiple liquids, okay, it will be basically d1 by mu1 plus d2 by mu2, if even if d1 and d2 are not equal. Okay, so this is the general formula. Even if you can extend it to more liquids. Okay, so if you have more than two, you can go on extending the formula. Okay, we'll use it in the next question. So let's move to the next question now. Question number 14 over here, similar to what we discussed in the previous question. Here we have a vessel of depth d. Okay, and we have two liquids, one with refractive index mu and the other one with refractive index 1.5 times mu. Okay, both of them half fills your vessel. Okay, and they are immiscible, of course, and the final apparent depth is 50% of the actual depth. Okay, this is the data that is given in the question. You are supposed to find the value of this mu. Okay, now I just told you to by heart the formula in the previous question. D double dash is equal to d1 by mu1 plus d2 by mu2. Okay, here d double dash is nothing but the final apparent depth, right, which is given. It is 50 times the actual one. Okay, here d1 is this distance. Okay, mu1 is refractive index of this one, d2 is this distance, mu2 is refractive index of the second liquid. Okay, so let's just substitute and find our answer. Okay, so the final apparent depth is 50% of the actual depth. Okay, so this final apparent depth is half of the original actual depth, right? 50% basically means half, right? 50 upon 100, which is half. So this is the apparent depth. The final apparent depth is half of your actual depth. Okay, so that is what I have written. And then d1 is again d by 2, mu1 is mu, d2 is d by 2, and mu2 is 1.5 times mu, right? So you can see d by 2, d by 2, d by 2 will get cancelled. So you have 1 is equal to 1 upon mu plus 1 by 1.5 times mu, right? So you can take mu common, take it to the other side. You have 1 plus 1 divided by 1.5. 1.5 is 3 by 2, so that will become 2 by 3, right? Reciprocal of that. So this is 0.67, so 1.67 will be the answer over here. So option D, 1.67 is the answer over here. Okay, so just remember this formula, that the final apparent depth in case of multiple liquids, okay, is given by this formula. Okay, so that's it from this question. Let's move to some mind-blowing questions now. So question number 15 over here. In this question, we have silvered a plane convex lens. Okay, so this question is based on silvering of mirror. Those who know it will do it easily, but for those who don't know, you'll have to take a deep breath in. Okay, so I know it's a bit tricky. Ray optics is in fact known for tricky questions in Bitsat, so do prepare well for ray optics. Okay, that is what I will say. So let's begin with this question. Okay, so plane convex lens, which is silvered on the plane side. We have an object which is placed at a distance of 40 centimeters from the lens. The focal length is given as 30 centimeters for this side. Okay, this curved surface. You are supposed to find where will be the image. Okay, so now since there is a silvering of lens, we cannot just do it directly. Okay, the lens formula is of no use over here. Okay, in fact this system acts like a mirror. If you see, we can break this system as a plane convex lens like this, okay, and a plane mirror. Okay, so this system we have broken it down into a plane convex lens and a mirror. Okay, a plane mirror. Okay, So now if you see, the ray will come from the object and be reflected from first get reflected through this lens and then strike the mirror, and then it will be again reflected and then again through the lens. Okay, so of course there is refraction, but I'm not showing it, but you can see that the net effect is like a mirror, right? There is reflection, right? So there is reflection, the net effect is like mirror, I'll say. Okay, so the system behaves like a mirror. When the one side of a lens is silvered, remember that the system acts like a mirror. Okay, now you can write the effective power of the system. Okay, so effective power will be power of lens. First of all, the incident ray passes through the lens, plus then it strikes the mirror, so power of mirror, plus again it goes through the lens, so power of lens. Okay, now you can write it in terms of focal length. Now remember one thing, that power of mirror is given as minus 1 by f. Okay, power of mirror is minus 1 by f, just because we have to maintain the sign convention that for converging mirror it should be positive, and for diverging mirror it should be negative. Okay, the power. Okay, so directly remember that the power for a mirror is minus 1 by f, and for your lens it's just 1 by f. Okay, so here we know that the final system that we have, system acts like a mirror, right? So the equivalent will act like a mirror, right? This is the equivalent system is acting like a mirror. So here the equivalent power can be written this way, minus 1 upon Fe, because it is acting like a mirror. Okay, now focal length of the lens 1 upon Fl, right? So power for the lens, this is the power for the lens. Again we have a plane mirror. Now for plane mirror we'll get this with a minus sign, it's a mirror, and then again we'll have this for the lens. Now just solve it. 1 upon Fe will give you 2 upon Fl, add this 2, and 1 upon focal length of mirror, right? Now for this one we have to find the equivalent, right? If you see, the mirror is a plane mirror, right? For plane mirror the r is infinite, so r by 2. The focal length is also infinite, so 1 by infinity, that is 0. So finally we have 2 upon fl is focal length of the lens is 30, right? So if you complete the sphere over here, yes, the focal length is on the positive side. Okay, so it is plus 30. Okay, so Fe will be nothing but minus 15. Okay, this minus sign goes to the other side, it's minus 15 centimeter. Now what does this mean? Okay, this means that this entire equivalent system, okay, this entire system will act as a concave mirror with focus length 15 centimeters. Okay, how do I know it's a concave mirror? From the negative sign. Okay, concave mirror has negative focal length, right? So yes, so this entire equivalent system will act as a concave mirror with focal length minus 15 centimeter. Now the question becomes so simple, right? We have a concave lens with focal length 15 centimeters, and the object is placed at 40 centimeters. Now just use the mirror formula and find the answer. Okay, so for v. Okay, so 1 upon f is equal to 1 upon v plus 1 upon u, or if you are smart, v is equal to u f upon u minus f. Now just substitute these values. Object distance minus 40, right, opposite to the direction of the incident ray, so minus focal length minus 15, concave mirror minus 15, right? And then you have minus 15 minus 40 minus 15, that is plus 15. So 40 into 15, that is 600. Okay, divided by minus 25, so that will be 120 divided by 5, and 120 divided by 5, 24. Okay, so option B, 24, is the correct choice over here. Okay, I hope you were able to understand it. If not, please rewatch it. Okay, so that is how you solve questions based on silvering of mirror. Let's move to your homework question, and then let's say goodbye. So question number 16 over here, it's your homework question. Okay, so you can pause the video over here, take a screenshot or make a note, and do give it a try, and do let me know the answers in the comment section. Okay, so I hope you enjoyed this video. If you did enjoy it, smash that like button. Also consider subscribing. Something new is coming up for Bitsat 2022, and this is how we end with a series. It was a lovely journey with you all. Thank you for all the wholesome comments that you made and all the support that you gave to a series. I know the average view count on a series videos is less than 100, but those wholesome comments, I really loved those. So thank you for the comments. Thank you for the everything. Thank you for the support to the series. Something new is coming up for Bitsat 2022. Stay tuned. I'll see you soon in the next video. Till then, keep enjoying physics.